Hi, my name's Rowan and I'm delighted to welcome you to Extreme Academy Live. We're absolutely thrilled that you've chosen to advance your career with us, with Extreme Networks, and we're going to do everything we can to make this an enjoyable and rewarding learning experience. And to that point, this is not just going to be about you watching a live stream video for a couple of hours. You're going to be able to interact with us in real time. So somewhere over my shoulder, there's going to be a QR code and a URL shown on the screen, which are both links to our Q&A app. So scan that QR code or type in that URL, go and check it out now. And the first thing it's going to ask you to do is enter a name. So just put a screen name in there. Don't put your email address. So if I was going there, I just put in Rowan, and that just gives us something to a name to address you by once we get into some interaction. Once you're in the app, then there's a few things you could do. You could ask a question. You could upvote a question. So if you spot somebody else's question, you think, yeah, I wasn't sure about that, I'd like to know the answer, then you can upvote a question, and what it'll do is it'll the more votes it gets, the higher it'll rise in the list, and our team will get to that quicker. You can also add a comment on a question. You can use that comment ability to answer a question, and the best way to reinforce your own knowledge is to teach somebody else. So if you can see something and you think, yeah, I know the answer to that, I can help them out, go ahead, go and give it a go. Help out the group and try and answer the question. Now, a really cool thing about this app is it can auto-translate. So if English isn't your first language and you feel more comfortable, especially on a technical subject, writing or typing in your first language, then just go ahead. Ask the question in your own language. The system's going to auto-translate it for us. We'll see it in English. The answer will come back to you in English, but then you've got a little bit more time to read and digest that answer. So if you've got two screens, what I recommend is you have the Q&A app on one screen, you have the live stream on another. If you don't have two screens, don't worry. You can run the Q&A on a phone. It makes a perfect, if you've got a smartphone, it makes a perfect companion app to as you watch the live broadcast. There's also a few other things in the app. There's a pulse tab. You can tell us how you feel. There's quizzes. We're going to be sending you some questions just for some fun, just to reinforce some of the things being taught as we go along. So behind the scenes, we've got a group of Extreme engineers. We've got some guests from our authorized training partners on our Extreme Academies. So big shout out to all of you for helping out. And we've got Claire and Dave, and Claire and Dave are going to be running the show. You'll hear them mentioned from time to time. The final thing, sorry, two things I need to tell you about. One is the recording. So as soon as we finish broadcasting live in whichever platform you're watching, then the recordings are going to be available on that platform. If you're watching in Vimeo, that's a great spot to go back to just to catch up. We understand that sometimes you have to leave early, something might disturb you, or maybe you can't watch it live at all because you're busy working or doing something else. If you're watching recorded, just bear in mind that if you ask questions, there's not going to be a team there who are answering in real time, but you can still post questions and we'll get back to you on a kind of best efforts basis. Final thing from me then is to introduce you to your instructor, to Isaac. And Isaac is the lead technical curriculum developer here at Extreme. So Isaac creates courseware, he creates courses that are used by teachers and instructors to train the engineers that are designing, building and deploying some of the most advanced networks in the world right now. So you can think of Isaac as the teacher of the teachers. He's got a fantastic passion for his subject. He's got some great stories that are going to help you understand the technology, and you're going to get to know Isaac over this course. I'm just glancing down at my monitor. I can see Isaac. He's absolutely raring to go. So that's it from me. I'm going to get in with the rest of the group. I'll be one of the people answering questions. So I look forward to hearing from you on the Q&A app. So Claire, we're ready to go. If you can run the graphic, bring up Isaac, and let's do this.
Thank you, Rowan. Thank you for that handover. I work in such a great team. There's so many people behind the scenes that have been working towards this, getting us to this point. Bethany, Claire, Rowan, Paul, Stuart, Dave, a whole lot of people in the back end who are going to be providing support for you. So thank you very much for that. I've been so anxious working up to this moment. We've been working on this for a number of weeks now, rehearsing, going over all of this, getting all the technology sorted out. As you know, my name is Isaac Diabreu, and I'm broadcasting today from Cambridge, the original Cambridge, not the one from Boston, the one where Isaac Newton invented gravity. And not only him, there were many others like Babbage and... Oh, okay. I've been told that Isaac Newton didn't invent gravity. He discovered it. Same thing. Anyway, we're not here to talk about gravity. We're here to talk about bits and bytes and WAN and LAN. And what a year it's been, right? What a year it's been. For some, really, really tough. For others, it's been a year of fantastic opportunities, with new businesses growing, with new businesses coming up with new ideas, and others, sadly, not so much, right? In the networking industry, in this industry in which I belong, we've been growing. Our business has been climbing because we connect the world. We connect you. We are in the networking business. We connect these systems together. We enable you to work from home. We enable you to work from wherever you are. Networking companies like us, that's what we do. And so this industry is one of those of terrible excitement, right? Because it's always changing, it's always evolving, and it's always renewing itself. There's always new things. So if you're one of those people, and there are, from the registrations we can tell, there are people here who are in dead-end jobs, right? When it comes to a Monday, you are like, oh, I can't go to work again. I can't do this again. I just push paper all day. I can't do this for the rest of my life. We know that there's those types of people. There's other people who have been doing whatever they're doing, and it's like, there's no satisfaction in this job. I can get no satisfaction. There's no joy in the job that you're doing. Well, you've come to the right place, because networking is one of those careers where it is so exciting. You can do so many things. It just never gets stale. It never gets boring. There's so many avenues that you can go into. So that might be you. I want to say to all of you who register, welcome. I mean, really, from my heart, welcome to this session. Sometimes you hear people say, you'll see an advert on TV, and or people say, well, this spray for your spectacles, this will change your life. Yeah, right. It's not going to change your life. In no shape or form. It's not going to change your life. But I honestly believe that this course, this training, has the potential to change your life. And I don't mean that lightly. I'm not advertising anybody over here, because what you take from this course, if you apply it, your life can literally be changed. And why do I say it could? Because of course, it still depends on you, right? I can't do the work for you. I can't write the exam for you. I can't study for you. I can't go and research, or I can't go and read books, or I can't go and ask your friends, or for you. You still have to do that. But if you learn from here, if you absorb from here, you literally have the ability in your hands to take this information and for it to change your life, to give you a career that you would enjoy for the rest of your life. For the next 40, 50, 60 years, you can enjoy something that'll give you pleasure, And it's done that for me. It changed my life. When I got into IT, it was fantastic. I mean, you can tell I'm passionate and I enjoy this game. But networking, when I got into networking and started to see with different eyes, right? Most of us, we type away on our browser and we browse here, we browse there, and we don't often think about what goes on behind the scenes. Hey, maybe you even work in a networking company, even like Extreme, and we've seen that, right? And when people get around the coffee machine, or used to get around the coffee machine and had conversations, they would talk about LANs and WANs and bits and bytes, and they would talk about these things, and you sitting there and you're going, yeah, the network's really slow today, yeah. But you don't really understand the language. You don't understand what it means. This course is going to help you. It's going to put you on a level where you understand the language, when you can participate and feel that you're actually adding value. So there's a lot to be gained from this course. Like we said, this is the first 2 hours of a 8-part series, 2 hours each. After the last one, you will have the ability to go and write an exam. And if you pass that, you'll get a certification from Extreme Networks that you can add onto your CV, onto your LinkedIn profile, and that you can use, right, in any job that you can apply to. I mean, I've never, ever in my life come across somebody who really knows networking and IT anywhere in the world who says, well, I can't find a job. You know, there's just so many different things that you can do when you understand networking. So I said to you, I started many years ago. My first computer had a monitor that was this deep. It was, you know, it didn't even have color. It was green, shiny things on the screen. You worked for 2 hours and your eyes got sore. But in just 20 years, 25 years, it has evolved to the point today that most of you who have a mobile device, a phone in your hand, we call it a phone, but it's actually not a phone. It's a supercomputer that has the ability to make phone calls. This industry has changed. There's been so much that has changed in the IT industry, in the networking industry in the last 20 to 25 years. If you're somebody who doesn't like change, who just likes to sit and do the same job day after day after day, this career is not for you. Networking is not for you. You'll get frustrated by the pace of change. But if you want to be somebody who grows and is challenged and wants to learn and do something meaningful, this is a fantastic career. And it doesn't matter if you're male or female, if you're white or non-white, the color of your skin is irrelevant over here. In fact, we need so many more women, for example, in this industry. And for some reason, so many women have shied away from going into IT and networking. And this is an absolute fantastic opportunity for you to jump in, because there is no reason that women are not fantastic at networking, brilliant at software, at careers in software and development. There's nothing to hold you back from creating a fantastic career for you as well. So networking underpins everything we do. From you know, when you go to a store, supermarket, and you pay with your Apple Pay or your Google Pay, that is enabled by a networking. The security that a bank has, that is enabled by good security. And everything by good networking. And networking is the foundation, the cornerstone for good IT, for good systems. And you can be part of that. You could say to me, oh man, you know, networking, I'm doing this because my friend said so, but I'm not really convinced. I'm more a maths guy, or, you know, a data, like a data analyst, a data scientist. Well, let me tell you, in a few minutes, I'm going to show you a video clip, and I'm going to give you a tease of a taste of the future of networking, of what it looks like. It's going to blow your mind when you can manage an entire infrastructure from a single pane of glass. But you will see from some of the data that we're going to show you that data scientists, data analysts are going to be working together, and are working together in Extreme, to take data points, to take information and turn it into machine learning and artificial intelligence. The careers that you can go into are fantastic, and those careers will enable networks to become more autonomous, to become smarter, to think, to make proactive decisions. So networking, we talk about networking, but the careers, think about esports. I mean, who would have imagined that nowadays you could fill stadiums with people who come in to watch gamers play games? My son enjoys watching the commentary on games more than he enjoys playing these games. So the careers that you can go to within networking are incredible. But it all starts here. It all starts when we understand the bits and the bytes. So get that pen, get that note paper or digital system that you have, get ready. After this clip, you're going to jump in and we're going to start up straight away with jumping into the networking course, and you are going to enjoy it. We are going to have fun, I promise you. See you on the other side of this. Right, let's jump right in and let's start with Extreme Academy Networks. So what's the purpose of what we're going to be doing over here? Well, the purpose, oh, by the way, you'll see me occasionally, I've got a camera in front of me, and so occasionally I'll need to look at my screen, especially when I need to read something. I'm not going to be teaching you by reading off screen. That's not the objective. Then that would be really boring. I'm not boring. But occasionally when I have to read statements, it helps if I look off screen. So if you see me doing this, don't panic. It's okay. I'm not trying to read the training material. I just need to focus. So the learning objectives here are to understand the purpose of networks and the principles to bear in mind when designing or managing them, right? So this is where we're going to go with the learning objectives. And so why do we need networks? Why do we need networks? Well, networks really are an enabling technology that enable us to communicate. Fundamentally, networking is all about communication. If you think about earliest man until now, we've evolved from the very basic form of communication. We've used hand signals, we've used fire, we've used flags, we've used drums. We've gone through so many iterations of the way that we communicate, even today, even though in most cases there's no more need for Morse code. In emergencies, you can still use Morse code as a way to communicate. When Marconi came around and invented radio, then we could start to communicate across massive distances, right? So radio was one of those things that really leaped and helped us to communicate. Alexander Bell with a telephone. Suddenly, instead of writing letters and waiting weeks for letters to arrive back, we could listen on the radio. We could talk on the telephone with somebody halfway across the world. We've evolved. We moved to satellites, and now we have satellites in space, and we can watch TV based on those signals that we get from satellites. Use GPS with those. It's all about communication. Nowadays, we also use fiber. So we've moved from having satellites, fiber. We've evolved so much in communication, and networks and networking enable all of those things. Networks are the things that enable us to take an image like you see on screen and to convert that into zeros and ones, transmitted across light, transmitted across wireless, the air, the atmosphere, and someone on the other side, on the other end of that, gets an image and they can see how that image is, right? Instantly. We use WeChat, we use WhatsApp, we use Messenger, and we send these messages, and it kind of just appears almost like magic. Every network that we're going to be talking about, every network has to have 3 components. We'll cover them in the slide. We have to have 3 components for it to be a network, right? The first one is we need to have a group of computers, a group of servers or devices that exchange information. People think of an iPhone as a phone, as an Android phone. I kind of think a little bit differently. I kind of think it's not really a phone, because if I think about the amount of time I spend on this device making phone calls, they really are a minuscule proportion. I would say that my phone is actually a computer that has the ability to make phone calls. So to have a network, you must have a group of computers or servers or other devices. Now, what do we mean by servers? What is a server? If this is new to you, you might have heard that term server. A server is not someone when you go to a restaurant who serves you your food. No, that's not the server we're talking about here. Most of you probably use a service like Gmail, right? And if you use Gmail, if you were Google's only client, you could be on your computer, you send a mail, it goes off to Gmail, and on Gmail, they could have had a single computer. And you could have picked up your email, received it, responded, one computer. What's a server? Well, Gmail doesn't only have you as a customer. They might have millions. In fact, they have billions of customers that use Gmail. And if all of us, or even a fraction, if 10% of us log on to Gmail at the same time to go and get our email or send our email, one computer is not going to be enough. You're going to need not even dozens or hundreds, but you're going to need thousands or possibly tens of thousands of computers to be able to do all that processing. So you're going to need a number of devices, computer, servers, devices, iPhone, to exchange information. You go to a store, you go to a Tesco, you buy something, you tap it with your card or you tap it with your phone, and that information is going to be carried across a network to some bank somewhere in the cloud somewhere. The network is going to bring back a little authorization that says, ding, your transaction has been successful. It needed devices on both sides to be able to complete that. The second part of what we're talking about here, the second component, is a common language. Okay, I said in the beginning that some of you are Spanish, some of you are French, some of you German, some of you are coming in from Brazil or Portugal or the UK, coming in from all over the world, and all of you speak your own native language. To many of you, English is a second language, but English is the language that I'm using, the common language, so that all of us can understand, right? Now, you might not understand English as well as your first language, but it's still a common language. If each one of us sitting on this call was invited and none of us spoke English, then I would be talking to myself, and all of you would be sitting there watching my lips move, but being unable to communicate back with me or understand what I'm saying. So for a network to function effectively, and I mean effectively, a network needs to have a language as well. It's not English. It's called TCP, and we will cover this in detail later. Transmission Control Protocol. It's a language. Computers need to have a common language to be able to communicate. Without it, we will struggle. The third component that we need to have a network, the core components that we need, are devices, infrastructure. If you're at home watching this training, you're probably watching it on your laptop, on a desktop computer. You might even be watching it on your phone, right? You might be tethered. By that, I mean you might have a cable that's going into a network point somewhere, or you might be watching it wirelessly, magically. But actually, you might have a device we call a wireless access point, WAP, a wireless access point at home with 2 antennas on it that broadcasts my voice, my image, my video into your room, into your living room, dining room, wherever you are. That's a device that's an infrastructure device, right? It's an infrastructure device. In the world of networks, our company, Extreme Networks, we make these types of devices, these wireless access points, switches. We'll talk about terms like routers and firewalls. You need that type of equipment as well. So 3 devices or 3 core components that you need to make a network, right? A group of computers or devices, a common language to join them all together so that they all speak the same language effectively, and then we need an infrastructure made up of things like switches, routers, etc. Now, why are they indispensable? During COVID, networking companies were part of the essential services. And they really are, because they've joined us in places and in ways that we couldn't do it if we didn't have it. Can you imagine right now if you don't have internet? I mean, you can't, I suppose you could, but I wouldn't be there in your living room or your lounge or your bedroom. I wouldn't, because we just couldn't communicate. So we need the internet, and the internet is just a network of networks. So networks have become really indispensable, not just because of COVID, but they enable education. They enable all of these things. Let's look at some of these. Social applications. I have a job today because someone came across my profile on LinkedIn in California, saw my profile, contacted me and said, hey, we're interested in chatting to you. So social networks empowered me to get a job eventually with Extreme Networks. This was done using networks, right? And networking and social applications. Business applications. If you work for a corporate, chances are really high that you use Office 365. You need a network. Without a network, you can't get to Office 365. You need that. And it could be other open source tools, not just Microsoft. Think about internet banking, right? When you bank, you transfer, you PayPal somebody some money, a transaction, you buy something off Amazon. That all is enabled using networking. If you trade in stocks, you're trading on the London Stock Exchange or New York Stock Exchange or Shanghai or whatever, you need a network. Networks power all of those types of industries. The healthcare industry nowadays. Before, doctors used to walk around with clipboards. Watch any TV series nowadays. Doctors all have iPads or tablets. Everything is digitized, and you take an x-ray and the doctor has it at his fingertips. How does it get there? It's not magic. We're using networks. Networks are the way that information gets to the doctor or to the patient just in time, just like that. Gaming. I bet there's a ton of you that love gaming, right? Xbox, Sony, Apple, whatever it is. All of that is enabled. So we have so many services, education, security. Think about security in a mall, in a shopping center. If you're in London, on the underground, we have security cameras. They are all powered by networks. essentially when we communicate. When I talk to my mum in South Africa, I communicate with her. I might be using FaceTime, but underlying that, that's all networks. That is all networks. So in this journey that we'll take over the next 8 weeks, we'll try and look at things like design, pre-sales, deployment, support, admin sales. There will be a course right at the end. This is course 1. It's 8 weeks, but we'll have a course 5 that teaches you some of these things, like now that I've learned all this networking stuff, how do I actually apply it? Can I get a job with this information? And we will help you to do that. When you design a network, you need to have a strong, smart approach, right? Most of us have built up networks at home, plug in a router over here, do this, plug in an access point, and voila, the thing works. Sometimes it's not voila, it's like, oh no, not voila, bad But that's the idea. So what makes a network good or bad? Now, think about your Wi-Fi setup at home. Is it good? Is it bad? You might say, well, it's okay until I go upstairs, then the signal sucks. Or, no, I really get a good access. It's enough for me. But think about, what about a wireless network in a hospital? What is good enough for a hospital? At your home, you could just say, oh, it's not working, go and reboot that. But what about a network in a hospital, a Wi-Fi? Can you just say, well, it's not working, just reboot the whole thing, just restart? The requirements for a network, when you build a network, are very different depending on the industry, right? It might not be as simple as it is at home. What about administration? In your home, you might be the only administrator. In other words, if a wireless router goes down, you go there and you reboot it, you do whatever, and it's all working. Great, you are the administrator. But what if you run a wireless network in a hospital, and the hospital is made up of 10 floors and has 500 beds or 2,000 beds? How do you administer that? How do you administer every access point? This is where we start to think, well, I can't just design it the way I design it at home. It's going to need more than that. I'm going to think about redundancy. I've got to think about failure. I've got to think about, what if there is a failure? What do I do? What if an access point dies? How do I get... So the answers to these things can be complicated and not as simple. But there's a few principles that every network, we spoke about core components that is needed, but there's also a few principles that we need to think about when we design networks. And you might be thinking, we haven't even started about networks and now you're talking about design already. It's like, where are you going with this? Stay with me. Don't get lost on this. Stay with me, because what we're trying to do over here is I'm trying to give you a big picture, and then we'll tunnel in and we'll start looking at the detail. But the big picture is 3 core components. We know what they are. Now, what are the principles? If I'm going to design in it, what are the security, right? Listen, when you do internet banking, you want to make sure that your banking is safe, that no one is siphoning off your funds that you receive from your boss or your pocket money or whatever it is. You want security to be really paramount. And every company nowadays is really paranoid about security. What's security about? Hey, keeping the good guys in and keeping the bad guys out. Right? So security, every network that you think about, even your home network, the idea that, oh, I'm just going to put in a wireless router over here and I don't need a wireless password, or I'm just going to make the wireless password because there's nobody else who's going to steal my data. Don't think like that. Those days are long gone. You need to be security aware. So everything that we do, even though we don't mention that, this is a principle that you have to remember, that you have to think about. Security. How is my network secure? Is it secure? And if it isn't, what can I do about making it secure? What about redundancy? Remember we said at home, well, if it goes down, you just reboot it. But if you're running a nuclear power station, you can't just, if it goes down, it goes down. Google can't just say, well, if Gmail goes down for a day, so what? They need to have redundancy. And what do we mean by redundancy? We mean a single point of failure. If Google only had one single computer to handle all their Gmail stuff, that would be a problem. It could even be a supercomputer. It would still be a problem because it's a single point of failure. If that computer fails, everybody goes down. It's the same thing when we design networks. If the environment demands it, because of cost, of course, you're never just going to have a single switch in a location for your company. You will have redundant switches, or you will have you'll have one plus another one that's redundant. So if one fails, another one takes over. In servers, you will find that high-end servers will always have more than one power supply on them. Some of them might even have 4 power supplies on them. And so if one fails, the other 3 can carry the load really easily. And if a second one fails, the other 2 will struggle, but they're still there. But what's the probability of 2 failing at the same? It can happen. But if you're paranoid, then you're going to have those 4 power supplies. So redundancy is another principle of smart networking. What about flexibility? If you've ever been to a brand new airport, it's only brand new for the inauguration, because a month after they've inaugurated and launched the new airport, you see cranes moving in because they suddenly need to expand this and they need to expand that and build a new parking garage. An airport is like a building site. They're always building, which means it's flexible. It's never a static. A network is never completely static. If you think about a company, you have 500 employees in a company, they start working, but tomorrow you might have 600, or you might have 200, and you need to scale back or scale up. So a network has to be designed with flexibility in mind. This is great for now, but how do we build it so that if we need to build a second office, we don't have to rip everything out and start again? We can just take on what we've got and build from there. Flexible. That's another principle that we need to use. The fourth one is cost. You can't just throw money at networks and say, well, it doesn't matter what it's cost. This one is 10 times more expensive than that. It doesn't matter. We got lots of money. Let's throw it at money at this. Networks, you have to always work within budgets, within constraints. And oftentimes the people that sign the checks, they don't quite understand the technology behind it. So you as a networking person is going to have to consider this, is going to have to consider somebody. You might say, I want to upgrade my network. The first question that they're going to say to you is, how much is it going to cost me? And you're going to say, well, it's going to cost you $1 million. And they're going to say, are you nuts? You're going to $1 million to upgrade 50 people. It's never going to happen. So you need to get the best bang for your buck when it comes to networks. And understanding how you can design a network implies that financially you have to think about these things. If we need redundancy, but can we do it this method or can we do it this method? This one is more expensive. This one is cheaper. They both have advantages. Can we live with the disadvantages of one over the other? So cost is an important factor when you design smart networks. And so is manageability. If you're in that hospital scenario and you have hundreds of wireless access points, you need to manage them. No network administrator is going to go around every single day to every access point to make sure that it's working properly, right? They used to probably do that in the old days. No ways anymore. Extreme Networks has a tool we called XIQ, Extreme IQ, Extreme Cloud IQ, where we can manage from a single location in your browser, just browse to a website in your browser, and you can manage a hospital's network with hundreds of switches, hundreds of access points, thousands of them, from one single pane of glass. Just like you log into Gmail and you see Gmail and you can manage your mail, the same thing. Extreme Networks is really advanced, pushing the envelope on what you can do, managing an entire infrastructure. And that's one of the principles as well. It's not just about putting up a network. Oh, this is a great company, let's buy all our devices from them, and then like, oh man, managing this is a nightmare. So manageability and the ease of manageability is really important. So I hope that this first module has helped you to see the importance of networks, how they've evolved from just pure communication one-to-one to Morse code to radio to satellites to fiber, and that you've understood some of the core principles, some of the core components of a network. Remember, it's devices, computers, servers. It is a common language that we need so that all these devices can talk to each other. And then it's infrastructure, right? Servers, switches, routers, cabling. Those are the three components of every network. And then we looked at some of the principles of smart design. We looked at security, finance, flexibility, manageability. These are the components that together they drive what we do with networks. So I hope that that's been really useful for you, and that you've learned something from this module. Okay, so for this section that we're going to do now, I'm going to try and do it in about 20 minutes to bring us up to 50 minutes. And we call this section Physical Connectivity L1, meaning layer 1. Generally speaking, when we try and understand networks, we use a model called the OSI model. Some people just use the word Aussie model. And it's this particular model that's made up of 7 different layers. Think about it as a slice of cake, that when you slice it, you see that there's 7 different types of fillings on it, if you want to do that. And generally speaking, in the academy course, we teach the OSI model, but generally it's kind of placed at the beginning. We explain the whole OSI model, and then we break it down into the individual layers. But today I want to do it in the reverse order. I actually want to start with the layers, and then at the end, when I've done the different layers that we want to cover, then I will cover, I'll do like a summary where I then explain the entire Aussie model, OSI model. If this kind of doesn't make sense to you, you can always, when you watch the recorded version, you can always start with that module and then come back to this one. The reason I really like this model is because this model gives you something that you can really practically learn. And we're going to do this later on. I'll have some exercises where you're going to practice this stuff. This stuff is really interesting. I really love teaching this particular module, especially this first part, where we're going to talk about binary, right? We're going to talk about something we call binary. But let me read the objectives of this lesson. So to understand the principles of physical layer operation, which is this layer 1 I told you about, and become familiar with various connection types and layer 1 related protocols. Okay, we're okay with that. So let's start by talking about binary. I suppose most of the people that are attending this session, that are watching the session, would at some point in their lives have heard someone say something like, all computers know is zeros and ones, right? And you might not even know what that really means, but you've heard it said. Computers just know how to do zeros and ones. And actually, that's true. That is actually true. They know how to do zeros and ones. That's how they add. The human brain is incredible, right? We can add in fives, tens, 50s, 100, a million. We can add in ones, twos. We can add in all sorts of things. But actually, we find it a little bit difficult to add or to calculate or to think in binary and zeros and ones. Now, what exactly do we mean by zeros and ones? Well, when we talk about the number system, sometimes we don't even consider this or think about it, right? If I were to say to a child, can you count for me, right? If I said to my son or my daughter when they were small, can you count for daddy? They would have started immediately with 1, and they would have gone 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yay! They counted up to 10, right? And as a dad, I'd be so proud they managed to count up to 10. And so we would call that base 10. In mathematics, they would say, well, that's base 10. Why? Because when you get to 10, you basically start again. So if you think about an abacus, it's got all these rows, and each of them have got 10 beads. So when you count the first 10 beads and you reach 10, then on the second row you add 1 bead in there, and that means 10. So you count to 10, slide 1 bead, and then you start again on the bottom row. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then when you reach 10, you put a second bead. So the base system, in mathematics we say the base system is base 10. But that's not the only one that we use, that humans use, that is really common. Think about time. If you look at your watch, it starts at 12 and it goes to 12 and then it starts again, right? Or if you use 24-hour format, it starts at 0, goes all the way to 24, and then it starts again. So it kind of resets every 24. What about our calendar? Our calendar is what? Base? Come on, type it in there. What's our calendar? Base 12, right? 1, 2, 3, 4, 5, January, February, March, all the way till December. And then what happens? Then we start again. Same as the year. We go to 1,000 and then we start again. So the world in which we live in is made up of many, many, many numbering systems, which we don't even think about that way, but they are base 10, base 12, base 24. But computers just talk about base 1. Base 2, which means a computer in base 2 can only have 2 digits, 0, 1, 0, 1, 0, 1. It can't have 0, 1, and 3. It can only ever have these 2 states, 0 or 1. Think about it as no or yes. Dad, can I have some Nando's? Yes, 1 in binary. Dad, can I have some sweets? Candy? No, a 0. Off, think of them as off and on. Consider a light switch in your bedroom. It only has 2 states, on or off, right? On or off. I mean, I know some people have a timer, but a dimmer, but the dimmer can't work unless it's switched on. So you could say that a light switch in your bedroom or in your home is a binary switch because it can only have these 2 states, on or off, on or off. Okay, stay with me. This is important. The reason I'm doing this now is this is important for a lot of stuff that's going to come in networking, right? You're going to understand this. So if you get this part, right? I want you to really focus in on this part. Make your notes, use the paper, use a pen, focus in on here, because this is an important thing. This is kind of a real foundation. If you understand this, you've done really well. So binary is what computer speaks, what computer understands, calculates, uses this to do everything that it does. Two states, 0 or 1, on or off, no or yes. So when I want to talk to somebody, right? If I want to talk to my wife, or I want to talk to a friend, or I'm going to visit a friend, and I might call them and I might say, hey, pizza, right? Pizza. I could do that with a WhatsApp message or Snapchat message. I could do that. Pizza ? And then I press send, and instantly they get that message. But in the back, what is actually happening? Because it is possible for me to record my voice saying pizza, 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 ? And then I hit send. So I could send voice, or I could just type it. Now, humans, we can communicate using speech and non-verbal cues. I could show them a slice of pizza, or Nando's, my favorite food, Nando's. Oh man, quarter chicken. Yeah, big time. So computer encoding, computer needs to change. It needs to have these techniques to convert human language to another kind of data, binary. So it needs to take the text, each letter, P, I, Z, Z, A, ? It needs to take every one of those letters and convert that into binary. So into a state of yes or no. That's what it needs to do with every letter. And if I were to record a voice message, it needs to break down that mechanical wave form into a series of zeros and ones. And this is what you look like. If you see it on the screen, that's what you look like. Pizza with a ? When broken down into binary, looks like that. It's impossible to read, right? 0 1 0 1 0 0 0 0 0 1 0. You can see that for humans, this system doesn't work for us. Binary is like, for us, that's no good. But for computers, perfect, because of its simplicity. So I say the word pizza, I type the word pizza, I hit send. My device, my iPhone, my Android phone, my tablet, whatever it does, takes that, converts each letter, each ? into a binary format, puts it on the wire, sends it across, and the pizza person on the other side like, pizza? Hell yeah, yes, absolutely, send, and it gets converted to zeros and ones and comes back, right? And what do? You get a smile. Nando's quarter chicken, extra hot. Awesome. So the other term that you will hear people talk about when they talk about binary, or how computers communicate using zeros and ones, the other thing is you'll hear people talk about bits and bytes. It's not like, a bit of Nando's and a bite of chicken. It's not that, okay? Bits and bytes. It's a way that we kind of describe this unit, okay? And so 1 bit is the smallest piece of information that a computer can actually send. 1 bit. Now, we've discussed this, right? A bit can have a value of 0 or 1. That's it. That's all 1 bit can be, 0 or 1. But a group of bits is a byte, right? So you take a small bit, a small byte, and it's the same as taking 1 big bite of that juicy Nando's chicken wing. So 8 bits makes up 1 byte. This is how we're starting to shape data, right? Bits and bytes. each bit can be 0 or 1, and 8 bits together create 1 byte. The byte is not 0 or 1. Remember, the byte is a container of 8 individual bits, and those bits can have this value of 0 or 1. So there on the screen you can see a byte, and it has a location. There's 8 of those from right to left, and they all have a value in that. We sometimes call that an octet. Okay, octet, 8, octet. A byte, of course, is made up of characters of the alphabet, and if you want to do some research, you can go and look up ASCII notation. So that's ASCII notation. Do a Google search and you will learn about the alphabet, how each letter of the alphabet is converted into a binary, and you'll learn about these particular values. And that's how I got that pizza, that long binary string. That's how I did it, by doing the search. So computer package these characters into words, right? And the people who design processors like ARM or Intel or NVIDIA, when they designed these, the smallest word size used to be 4 bytes. 4 bytes, well, each byte is 8, so that's 32 bits. And that might ring a bell, because sometimes you would have heard of people saying things like, oh, Windows XP is a 32-bit operating system, but Windows 10 is a 64-bit operating system. So when they design processors, the common minimum word size nowadays across Mac, across Windows, across Linux, is 64-bit. In other words, 8 bytes that make up, that's the minimum word size. Okay, so if I see a table like this on the screen, how can I understand that? Now, in this table, you will see that on the yellow section, I have what we call the bit position. So 8 bits. On the right-hand side, we call that the least significant bit. And on the left-hand side, we call that the most significant bit. So think about it like this. If I have the number 1,000,001, what's the least significant bit, right? The least significant, well, that would be the smallest number. And other than Arabic writing and Hebrew writing, where they write from right to left, if you're writing from left to right, which is the smallest value in 1,000,000 to 1? It's the value on the right hand side. So that is the least significant value, the least significant bit. And on the left-hand side, that is the most significant. So that's important, the least and most significant bit, okay? So this, the yellow part, is the bit position. And above that, the blue is a value that we give it. Within the byte, we give each one of these bits a value. So the first bit here, 2 to the power of 0. Anything, any number to the power of 0 equals itself. So 2 to the power of 0 equals 1. 2 to the power of 1 equals 2. 2 to the power of 2 equals 4. Remember, we are on a base 2 mathematical system. So by placing these bits in these specific locations, we can then assign values to them, numbers to them. They 2 to the power, each one of them raised to the power, right? So 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, to the 3, to the 4, to the 5, to the 6, to the 7. 8 of them in total. And these are the values that these things represent. So 2 to the power of 0 is 1. 2 to the power of 1 is 2. So look at what happens over here. Each one of these doubles. 1, double is 2, double is 4, double is 8, 16, 32, 64, 128. So in a byte, the most significant bit is on the left-hand side, and it has a value of 128. And the least significant bit is the one on the right, and it has a value of 1. Now you might be thinking, but why is he doing this? Because within a byte, we need to have the ability to assign a value to that byte. Each bit can only have a value of 1, but a byte, depending on what you switch on and off, can have an overall value. So let's see the number 243. If I wanted to represent the number 243 in binary, this is how I would go about it, right? So in a byte, I want to represent the number 243, which could be the letter A, or the letter Z, or the letter B. But if I wanted to represent it in binary, this is how I would do it. Okay, so 243. So I would start off with the biggest number that I have, 128. That's the biggest number I have. And I would change that. I would switch it on. So switch on that bit to the 1. So the value of the most significant bit is 128. I switch that on. Here's a running total over here. Then I go to my next bit, okay? The bit position. This is the number 7-bit position. And if I turn that one on, it has a value of 64. So 128 plus 64 equals now 192. It's still not 243. So I got to keep going. Now, do I turn on this one? Do I turn on this bit position number 6? If I turn that on, that's 32. So does 32 plus 192, is it less than 243? Let's see. If I turn it on, right, then it is a value of 32. And if I subtotal it, there we go. It's going to 224. Is that less than 243? Yes. So I got to keep going. Right, what about the next one? What about this bit over here? Because if I turn that on, it's going to add to this value 16. And if I add 16 to that, that'll bring it up to 240. So is it less than 243? Let's check. Yep, I go to 240. Still less than 243. So what's the next stage? Well, the next one is this bit over here, which is 8. If I turn that on, then 240 becomes 248. So I can't turn that on. So to represent 243, I'm going to have to switch that bit off. I remain at 240 because it has a value of 0. What about the next one? Well, the next one has a value of 4. If I add the value of 4, it's going to go over 243. Not good. So that bit also has to be turned off. What about the next bit? Remember, turned off, still 240. The next one is a 2. Yep, if I turn that on, 242 is still less than 243. And if I want to get 243, I need to turn this bit on as well. So now I have the number 243 represented in binary. And now 243 in computer language is 11110011. Here's an exercise for you. What is the maximum number? If I turn on all of these, what's the maximum number that I can represent in 1 byte? In other words, if I turn every bit from a 0 to a 1, if I switch on every bit, what is the maximum number that I will get to? Think about it. write it down. We've reached the top of the hour. We're going to have a break now, and we'll be back in about 10 minutes' time. So, Claire, if you can just take it away. We're going to have some, adverts and some video clips. Feel free to watch. Feel free to go on a toilet break or whatever you need, and then come back and we'll continue from here. I hope you've enjoyed this.
At the University of Florida, we talk about creating a championship experience in everything we do, and it starts with our student athletes. But it extends to Gator Nation and our wonderful fans. Anytime you're in that environment where you're hosting a lot of people, you want to make sure that you remove as many barriers as possible for people to be engaged, both with the university and also with friends and family. And hopefully through those connections, it creates a mindset where they can't wait to get back up here the next time they have an opportunity to come cheer on the Gators.
There were several primary business drivers to investing in Wi-Fi here. The first was solving a problem that we had, just generally speaking, with our fans. Our fans had told us for years that one of the issues of coming to our stadium was that the connectivity was bad, and we were aware of that. And when you have 90,000 people in a stadium, things like that are going to happen. The reason why Wi-Fi is important for us is because it's important for our fans. And I think at the very basic level, not having Wi-Fi in our stadium takes something away from our fans that have a normal daily life.
You have so many people in such a small area, cellular data is useless, and you can start feeling that probably 2 hours before the game. Working with Extreme Networks has been fantastic. They've been with us from beginning to end, and then after close out of the project, they're still there, still checking in, and being able to have them now deliver this stadium project for us has been exciting and fun to be able to work with that group and people that you've known for a long time and trust, and I think that's been a big deal for us.
The most exciting thing for me is knowing that there's so many more technologies available out there that we can implement in our stadium that we don't have a barrier to because of our investment in Wi-Fi now. The partnership with Extreme has been phenomenal, have met our needs both in terms of timelines and in terms of the communication, and we couldn't be happier with the partnership.
The response has been phenomenal to the fact that our fans can now get on our Wi-Fi system here in the stadium and stay connected, enjoy all the things that they are able to do when they're not at the game, but they get to do it with their family and their friends while cheering on their favorite football team. So it's been a really positive, and not just positive from the standpoint that they have access to it, but the way the system performs at such a high level, and we could not be happier with the system that we got from Extreme and the way it's supporting our fans here at Ben Hill Griffin Stadium.
Ga ik terug naar 1997, naar de eerste editie, waarbij we met een grapje zijn begonnen. In de zin van, we gaan in een weiland een beetje crossen en dan gaan we een feesttentje naast zetten. En dat was zo'n succes. We kregen de smaak te pakken, we wilden groeien, we wilden meer. En zo is het festival heel langzaam gegroeid.
Zwarte Cross is one of the largest outdoor music and sports festivals in Europe. We have been providing the Wi-Fi network really to offload the data from the public 3G, 4G network. Together with our partner Indicium, we're trying to enhance the user experience.
Hier realiseren is eigenlijk het hele draadloze en bekabelde netwerk. Het grote voordeel hiervan is dat de veiligheid geborgd is. En daarnaast zien we dan ook dat mensen 4G gaan gebruiken. Dus de mix eigenlijk van 4G en draadloos netwerk gebruikt.
Imagine a green field where cows are feeding themselves for 144 acres and you have to set up an event including so much IT as we do here at Zwarte Cross. You have to have a lot of glass fiber to host people, to scan 2,000 people per gate per hour. So we have 9 gates, so you have 80,000 people are able to enter in the area. Those are challenges because there's nothing here.
This year introduced a few new analytic systems that Zwarte Cross is using to understand what are the trends on the network, what are the issues on the network, or how the network is performing during the festival days and before. What it does effectively is it looks into all of the traffic for all of the clients, what they're doing, when they're doing, and how much traffic they push, what applications they use. You can see that the network response and application response very stable.
This is of course a great hospitality event. We're providing the best connectivity in festivals like this because people more and more want to be connected with the people at home, their friends, their family, and we can help the organization there to give all the visitors better experience.
So for this year, we are also providing our Extreme Guest solution. When they connect to the free Wi-Fi network here at Zwarte Cross, they get a nice splash space where they can just click on accept and connect.
They are moving all the time, and this is what we can understand here as the dwell times by the hour of the day, by the day of the week. We know how many of them are new users that just came in today, how many of them have registered, for example, yesterday, and this is the returning connection.
Last year we did about 5 terabyte of data transfer across our Wi-Fi into the internet. I'm very glad to have a technical partner like Extreme Network to help us solve these issues we encounter every year.
Je wil weten waar mensen uithangen, je wil weten hoe mensen zich registreren, je wil weten hoe voorraden worden bijgehouden. Dat betekent dat techniek eigenlijk onmisbaar is. Sterker nog, als de techniek uitvalt, kunnen we haast niets meer. We hebben een partner, Extreme Networks, die ons daarbij ondersteunt. En daar zijn we ontzettend trots op, want daardoor hebben we het wel voor elkaar om voor iedereen dit hele mooie feest mogelijk te maken.
Hey, welcome back. Part 2 of today's course. 1 hour to go. I hope you've enjoyed it so far. I've enjoyed being here. Before the break, I gave you an exercise, and I asked, what is the biggest number that you can get in a byte? So in one byte, if you were to take each one of the values, each one of the bit positions, right, with their relevant values, and you were to turn that bit position to on, so in other words, enable it, turn it on, each one of them, all 8 of them, what's the biggest number that you would get, right? That was the exercise. And from the chat that I saw during the break, I think that most of you actually got it right, which is absolutely fantastic. But just in case I missed some, and just in case some people didn't quite get the question or perhaps didn't get the answer, I'm going to go over the answer now, and we'll switch over to the whiteboard, and I'll go over that answer with you and how we got to that actual calculation. So let's jump in. Let's take a look at how we calculated this. So if you look on screen, I've written over here the same as is on the slide that you had in front of you a couple of seconds ago. And so we said, the question was, what happens if we turn each one of these into a 1? We switch on all of these, right? Remember, we said down the bottom here, this is the bit position, right? That's the bit position. Position 1 is over here, and position 8 on this side. And we said this is the least significant bit, and this is the most significant bit. But that's just bit position that we're talking about over here. Then we said, okay, so even though we can only have 0 and 1, we still need to be able to count. We still need to be able to do sums and calculate and stuff like that. So in normal decimal, we say 10 plus 10. So in binary, how do we do that? Well, we have to find a way that we can take the 0 and 1 and mathematically add values to them so that the computer can do this calculation for us, and that we can translate decimal, into a system that the computer can understand. So we said that on these, on bit 0 or bit 1, we raise that to the power of 0, and that equals to 1, and the next one to 2. And we saw that as we went through these, they double. Each one of them doubled as it went from the least significant to the most significant. So I think most of you actually got that. So now we've put a 1 in each one of these over here, and that is representing these values here. So if I sum up this and this and this, if I sum all of these values together, which is the same as going here, here, and summing all of these up, I end up with a number, and this is what I saw most of you had, 255. So 255 is 128 plus 64 plus 32 plus 16, etc., etc. That's how you got to 255. So for those of you who got it right, fantastic. For those of you who didn't get it right, now you know how to do it. And for those who didn't bother to do it, well, this is important, and it would be great if you get to master this, because this will help you, right through networking, right through everything to do with IT. Now you're sitting there and you're saying, okay, Isaac, so you've told me about binary, you've told me how computers only know how to count in zeros and ones, and now I can kind of look at a number and I can break it down myself. So that's really good. That's great. Next time I go to a dinner, I can tell people about this. But I can see your brains going, right? I can see inside your heads, and the gears in your head are going, and you're going, but if I had a value of 256, how would I do it? I mean, how does a computer come up with 256, right? Because you've just told me that a byte can only do 255 maximum. Man, I'm so glad you asked, because I have the answer just here. You remember when I said to you that when big companies like Intel, Nvidia, ARM, when these guys design microchips, and for many years in the past, right, they designed, we call that 32-bit chips. So the chips were able to receive instructions in 32 bits or 4 bytes, because 8 times 4 is 32. That's what computers use to do calculations. You address them in 32 bits at a time. I also mentioned that newer operating systems like Windows 10, OS X, Linux, for example, or even iOS, are 64-bit operating systems. So they can address much bigger numbers much quicker, right? It's the way that computing has gone. But whether it's 32-bit or 64-bit, it's not just made up of 1 byte. 32, 4 bytes. So in this example, I'm going to say, this is a 4-byte example. So that was byte 1. Remember, there's 4 bytes in a 32-bit operating system. So here is byte 2. Now look at this interesting thing here in byte 2. We still have 8 bits, right? We still have the 8 bits, and from the least significant to the most significant. So we still got 8 bits in byte 2. But now the bit position is bit position 9, 10, 11, and increases. And when we raise it to the power, you can see we were 6, 7. Now we just keep going. 8, 9, 10, 2 to the 11, 2 to the 12, and on we go in that direction. And above that in red, you can see that in byte 1, the numbers simply doubled. So 16 to 32 to 64 to 128. And now exactly the same thing happened. So there we go. 256 is double 128. And 512 is double 256. And 1024 is double. And off we go. In each one of these blocks, we double the value. So how does that help me? Well, if I'm looking for the number 256, look at this. I have 128 here, and that doubles to 256. Remember, 255 was the maximum. So if I wanted to write this in binary, how would I do it? Well, I would go like this. I would go 0, 0, 0, 0, 1. See that? 1, because it turns on 256. And now in this byte, what I would do here, I would take all of these off. And I would then go and say 0, 0, 0, 0, 0, 0, 0, 0. 256 in binary looks like that, with 16 zeros and 1 bit switched on. Make sense? Now, what if I wanted 257? Think about it. I'll give you 10 seconds. Got it? Okay. So your answer should be 0, 0, 0, 0, 0, 0, 0, 1, which makes 256. And then here, that should be 0, 0, 0, 0, 0, 0, 0. And then the last bit over here should be removed and replaced with the 1. 257. And I can make any number in binary. Listen, that is absolutely fantastic. And I think, you know, when you walk away from this, you can now sit down at any dinner table and say, ha, so when does 2 equal to 11? People are going to say, never. And you're going to say, well, let me show you. If I put a 1 there, and I put a 1 there, and I put 0, 0, 0, 0, 0, 0, what is the value of that? Oops, I said 11. No, that's wrong. 11 is equal to 3, not 2. I'm so sorry. So 11 is equal to 3, right? Because that represents 1, and this 1 represents 2. So these two together would equal to 3. So 1, 1 equals 3, and you can prove it in binary. Okay, cool. Let me put that aside and now go back to my slides. Okay. So we're now at the point where we've said that we understand computers talk in zeros and ones. We understand that that they can do anything. It's really fast to do, but it's like, but why is that important? Why is that a deal? So what? So they can do zeros and ones. Yes. So what? What's a computer gonna do with zeros and ones? I mean, yeah, okay, it converted it. Now what? And I'm so glad you asked that, because here's where the magic is. You've heard of electricity, right? Yeah, you heard of it? Mm-hmm. So let's look at what electricity does for us. Any electrical circuit is going to have a positive and a negative. Okay, if you think about a battery, even something like a battery right here, you'll see on the battery, on the copper side, it says plus, and then that side is obviously the minus. So you have a positive and you have a negative in a battery. On electrical circuits, the same, right? When you go to your light switch in your room and you switch it to 1, you switch it to positive, boom, you have light. And you switch it to off, to negative, boom, and the light disappears. So when we have a series of zeros and ones, we can convert them into electrical signal that we can send down a copper wire, copper cable. So the whole purpose of this, of converting everything into zeros and ones, is because we transmit data using electricity. Inside a computer, you switch it on, it's full of electricity. It's low current, but it's still electricity, right? And that's all you need to shift these electrical signals around. So if I put a positive signal this side, it's going to come out the other side as a positive signal. And if I put a negative, it's going to come out as a negative. So if I put out a positive and negative, if you look at this example over here, 1, 0, 0. So 1 is a positive, right? So a positive signal, and 0 is a negative signal. 0, 0, 0, 0, and then it's 1. So you can see over here in this example that I could take infinite amount of bytes and bits and just push them down this electrical cable. The electrical cable obviously is going to have some positive and some negative, and it's going to send that signal down, and someone on the other side is going to receive that. A network card on the other side of your network, your local area network or wherever, is going to receive that and going to do the invert, and is going to invert it back from an electrical signal to zeros and ones, which can then be converted into language that you and I talk. So that call pizza, 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 zeros and ones, electrical signals coming out zeros and ones back to pizza. Yeah, baby. And that's how this thing works. So that's the key. This is a beautiful, this is, to me, this is absolutely magic. So now that we've done that, we've talked about quite a bit of terminology, binary, bits, and all things like that, right? Bits, bytes. Now we're going to go a little bit deeper into that, because if you're going to be involved in networking, you're going to have to learn a language, just like you learned English, Italian, Portuguese, fala Portuguese. Just like we learned languages, you're going to have to learn a language. And trust me, computing has tons and tons and tons of acronyms and names for all sorts of stuff. But it's not as complicated as you think, as you think it might be, right? So we're going to look at a table like this. Now, how do you measure bits and bytes? Because we talk about kilobits or kilobytes, we talk about megabits or megabytes, or gigabits or gigabytes. You know, what do we mean by these terms? Over here, you'll see I'm referring to kilobit, megabit, gigabit, terabit. So kilo, giga, tera, they're used to describe large numbers, right? Because nobody's going to go around and saying, oh, I have a hard drive that's 14,368,272,400,000. No one talks like that, right? We don't talk like that. It just doesn't make any sense at all. So we use these terms, just like we use a liter and a kiloliter and a milliliter or a kilogram. The same type of stuff. Kilobit is 1024. Why? It's 2 to the power of 10. So we go 1, 2, we double it, 4, 16. And if you go to double it, if you get by 2 to the power of 10, it's 1024. That's why when you go out to buy a 1 gigabyte hard drive, it's not actually 1 gigabyte. It's 1.024 gigabyte. It's a little bit more, just because every number of these always needs to be divisible by 8, right? Because it's 1 byte, and that's done by 8 bits. So here you can see the type of data and the amount of data and why we use these terms, terabit. Imagine trying to tell somebody, that you've got a hard drive that's that bit in size. It doesn't make any sense at all. So this is what we do. But people often get confused with these values, and that is because we have kilobits and kilobytes and megabits and megabytes and things like that. But sometimes you'll see these same terms, but the suffix is PS, right? PS. And that means per second. It's not the same thing. It's like one is weighing kilos and another one is weighing or measuring kilometers per second, right? It's kind of that. So one is about how much data are we talking about here, and this one we're talking about bandwidth. We're talking about speed. That's what we're talking about. When you sign up to an ISP, generally one of the first things they offer you is they give you a range of choices, and they say, would you like our 20 megabyte per second service? And we have a 30 megabyte and 50 megabyte and 100 megabyte. And if you pay us, £50 a month, you can have a 300 gigabyte per second connection. What are they talking about? They're talking about how much bandwidth you actually have. It's very easy to remember this as an analogy. Just think of, I live in Cambridge, and there's a lot of little villages around here where they have a single road running through the center of the village, and it's really narrow. You can't go fast even if you wanted to, because you just can't. The road is really narrow. It's not wide. But I've been to Texas, for example, and the roads there are phenomenally wide, huge bandwidth. So what do we mean? Well, we mean that when you have huge bandwidth, you can send so much more traffic at the same time, because you can fill all of those lanes with cars. And so instead of just one car winding its way through the center of the village, if you have a lot of bandwidth, you can have tons of cars, much more. And that's people interpret that as speed. So you click on a web page and it might take you a few seconds to load, right? When I lived in South Africa, it would take you a long time to load. But at today's speeds, when you click on a web page, it's almost instant. It's just absolutely brilliant, right? And that's because you got a lot of bandwidth. So one thing measures, when you see PS at the end, that means you're talking about speed, measuring speed or measuring bandwidth. When you don't see that at the end, we're measuring data, either kilobits or kilobytes, 1,000 bits or 1,000 bytes, gigabytes, megabytes, etc., etc. So are we good on that? I hope so. Kilobits, add PS, it's kilobits per second bandwidth. Okay. Now, there are various types of communication mechanisms, okay? And I'm going to show them to you and teach them to you simply by giving you real world examples. The first one I'm going to show you is what used to happen when I was a young person, like a teenager or whatever, and I made trouble. And my mom, Portuguese mom, would she wasn't happy. This is the type of communication that happened when my mom wasn't happy, right? It's called simplex communication. In other words, I keep quiet and all she does is she just talks. Some of you are married, you know about this type of communication, right? She talks, my mother talks, you listen, you keep quiet. Simplex. These types of communications, they've evolved, right? They haven't always they started off like this, but you'll see as I go along that they have evolved. So this is what we call simplex, in one direction only. This second one here, which we call half duplex, this is how polite British people communicate, right? Imagine two cars going through this little village and one bumps the other one, right? In Britain, they get out and the one guy apologizes. Oh, I am so sorry that I bumped into your car. I wasn't concentrated. It was my. Please let me pay. And the other guy said, no. It was my fault. I was on my mobile phone and I was texting and I didn't realize and I suddenly hit brakes and it's totally okay. Let me pay. No. It's my fault. I hit you. No, I insist. I have no, don't worry. What happens in this case? It's half duplex, meaning I talk and then you talk and then I talk. Half duplex. So we went from simplex to half duplex, and then we went to Isaac's Portuguese way of talking, right? When my family gets together at Christmas, when all my family gets together at Christmas, this is what happens. We all talk, we all shout, we all listen, all at the same time. And the system is so good that the IEEE has adopted this, and most networking companies today, this is the way that their network cards and networks work. They talk full duplex. So I talk and I listen at the same time, all modeled on Portuguese behavior. Fantastic. So I'll give you a minute to read that. Okay, so when thinking about networks and designing networks, this is what we're going to be doing next, and thinking about these things. We need to define what type of network, what's the use case, where will it be used, how will it be used. So to do that, we have to start understanding topology, network topology. What does topology mean? Well, it means the landscape. What does the networking landscape look like? The first one I want to introduce to you is something called LAN, a local area network. The overriding characteristic of this is that it's usually associated with a fixed, small, generally we would say small area. Now, small could be your home, the network in your home. It could be in an office with 50 people. It could be in a small office, home office type situation with 5 people in there or 5 devices connected in there. We would define that as a local area network with various machines connected. Either they connected with physical cable, an Ethernet cable, or they might be connected wirelessly, and we will look at that in the next slide. And the types of speeds that we would look at there, maybe from 1 gigabit to 10 gigabits per second. Ethernet, if it's wired, generally like it is here in a local area network, if it's wired, we're using copper cables over Ethernet. You've probably come across this if you're a gamer and have gone to LAN parties and stuff like that, or involved in esports, then you would probably know that these guys put up all these machines and everything is connected using an Ethernet connection because it's really reliable and really fast. You could use fiber optic as well, but generally speaking, local area network, cheap, copper, because that's the best. Maximum distance you could go from a end to end to where you get to the switch, 100 meters. That's it. After that, I mean, it can still work, but it's not reliable anymore. Local area network. Next one is kind of exactly the same as a local area network, except when you look at that picture, you'll see that there's now some wireless in there. So a wireless area network, still part of a smallish location. When I say small, what I mean is it's not like a hospital, okay? It's not like an airport. which is absolutely massive. No, we're talking a smaller type of a network, small fixed location, floor building, etc., etc. In wireless LAN, you can have various wireless LANs existing within the same with the same access point. So one access point could actually have multiple wireless networks running on it. Now, how does that work? Well, when you get a wireless network for your home and your ISP sends you a little box, they generally have a default wireless network on there. Okay, it might be called, home network or something to that effect. But you do have the ability, oftentimes, especially in enterprise stuff like Extreme Cells, to go and create other wireless networks. So you could create a wireless network at home for yourself and for your family, and you call it, Isaac Residence Network. And then you could create another one called Isaac's Guests, and you can have both of them broadcasting from the same access point. Why would you do that? Well, you don't want your snooty friends to be able to come in and snoop on what you're doing, and get access to your printers and print all their birthday invitations off your printer. You might not want them to do something like that. So you would separate them from your own from your own network. We refer to those different networks, we call them SSIDs, and they stand for Service Set Identifier. That's what they stand for. When you don't know the stuff, you go to someone's house and you say, what's your network ID, or what's your wireless password? If you don't know, you say, what's your wireless password? If you are in the industry, if you're a networking guy, and I'm hoping all of you guys from today onwards, when you need to know this information, you just say, what's the password for this SSID? And the SSID could be whichever one comes up on your your device, your iPhone or your iPad, when you want to browse the network. So generally the technology we use here is not Ethernet, although there might be some Ethernet, like from the wall plug to your little modem or router or whatever it might be, but it's 802.11, and we will cover this in much more detail as we go along. And you have different speeds as well that you can get from there. It's never going to be as fast as a Ethernet connection. Certainly if you have many people, in your home, then the connection speed goes down because everybody is sharing the same bandwidth. So we have LAN, we have WAN. Another type of one that that is really popular, and you will understand this, is what we call a campus LAN. So when you think of the word campus, you think immediately of a university, you think of a location where people go to study, pre-COVID, right? Pre-COVID, that might have various buildings, right? On a property owned by a university. So one big campus, one big physical geographical area, and on there different different buildings, and each one having a different faculty, for example. So in this example over here, you'll see that I have 1, 2, 3 LANs, and these 3 LANs are all joined together into a data center. So these 3 LANs, Faculty of Medicine, Faculty of Sciences, Faculty of Physics, for example, but you have a data center, and all of these are connected into the data center. And what's a data center? It's a location where you would host most of your infrastructure. So your big switches, your servers, your mail servers, the really big heavy equipment, heavy in terms of, that can carry a lot of load. This is what we mean by a data center. And so generally a campus LAN is typified by the fact that you have neighboring buildings all connected using fiber optic cabling. And I say fiber optic because it's pretty rare that you're going to have 2 buildings connected together using copper cable, because you only have a maximum distance of 100 meters. And also, you generally, when it comes to connecting buildings, we always use fiber optic cable. Very reliable, and it can go long distances, right? Those are definitely the area. Again, speeds, from 1 to 10 gigabit per second easily to run within a campus network. The next one that we're going to cover is a metropolitan area network. Okay, a MAN, not a male, a metropolitan area network. We're not being sexist, that's just what it stands for. And this is when you have a network, for example, a campus, which is a group of LANs connected together across not just one campus location, but now across a city. So you could have, in a city like London, the University of London might have 4 or 5 different campuses in very different locations. 5 miles this way, 10 miles that way, 8 miles that way. You have campuses, they all belong to the same university. So when you have organization, it could be an enterprise, any, computer company, for example, and you have offices in different parts of the city. Take an IBM, that's such a big company. They would have something like this, metropolitan area network, where they can connect all their buildings to a data center. All the buildings are connected via fiber to the data center, but the buildings are not in one geographical campus. The buildings are in different parts of a city. Generally speaking, they wouldn't own the connections between them. They would generally farm that out to someone else, meaning they would have a subcontractor, another company that they would pay to run these links and connect all of them together. Speed, 100 megabit per second to 10 gigabit per second between the actual campuses themselves. Again, Ethernet, most probably Ethernet, and if they're using fiber, they can literally go thousands of kilometers. So we have LAN, we have WAN, we have a campus area network, I think is what we call it. Oh my, campus LAN. Okay, campus LAN, and then we have a metropolitan area network. Sorry about that. There's a lot to read. The other one that's really important and I want to cover, and you don't see this very often because this is a really huge organization. Now, take Extreme Networks. I mean, we're quite a big company. We're not on the scale of an IBM, but we're quite a big company, and we have offices in California. We have offices on the east coast of America, Salem. We also have offices in Reading in the UK, and we have offices in India. So we have geographically dispersed offices, and this would be called a WAN when you have physical connections between all of these different locations, between different countries, but it could be even cities. If you think about the US, it's so big, there could be thousands of kilometers between the cities, but many times this refers to countries, right? Networks that you have between different countries. Again, who owns these connections between them? Oftentimes, unless it's like government or NATO, an organization like NATO, you probably find that these are owned by companies and third-party companies, and then the enterprises would just rent those lines from them. So if it's military, they probably own all of this end to end. Again, from 10 megabit per second to 1 gigabit per second, and maybe even more for these undersea cables. These undersea cables, literally go for thousands of kilometers, and they just put fiber strands inside these big, thick cables that they lay on the bed of the ocean, and they crisscross the continents. The next one that we're going to cover is something we call a VPN. Now, during the time of COVID, you might be using one of these right now at home to connect to the office, and it's like being in the office. When you're on a VPN, it's what we call a virtual private network. So it's virtually private, right? Because once you're on this network, you can access all the resources. So I'm sitting here in Cambridge, back at the office in Reading. There are certain resources that I cannot get to unless I use a VPN. So if I need to get my mail, I don't need the VPN. I can just pick up my mail because it connects to the internet. DNS sends me to my mail server and I get my mail. But if I really want to get, HR, my data and things like that, I'm going to need to get a VPN connection. And a VPN connection is a secure connection where you are connecting into a cloud service, into an internet service, your ISP or whatever, and you then establish a tunnel, a VPN tunnel, virtual private network. Think of it as a tunnel that's coming from Reading, from the office in Reading, and it's coming from my house in Cambridge, and they're meeting and they create this tunnel. And any data that I send within this tunnel is encrypted and nobody from the outside can see that. So this is what a lot of companies are using at the moment for home workers. They set up VPN tunnels. Software, you can set it up via software. Mine is done via that. Or you can have a specific device, hardware device, that establishes a connection between itself and another hardware device in Reading, and you can have hardware tunnels established that way as well. I'll give you 10 seconds to read through this. And so what we're going to discuss now is looking a little bit at Ethernet in the beginning. So as so many things came from Xerox, Xerox PARC, including the mouse and the GUI and things like that, this also had its origin there, Ethernet. Ethernet, we'll cover that now in more detail. Is quite an old technology already, 1970s. We're still using it today, so it's really a long life technology, and it's going to be with us for many, many more decades. So again, like anything else in technology, it evolved from something that was really slow and got faster and faster and faster, and today we're getting 10 gigabit per second Ethernet connections, and it's like, yeah, I can buy those for a couple of dollars or a couple of pounds. So the technology's got better and better. This is a diagram of the very original Ethernet card designed by a guy called Bob Metcalf, founder of 3Com. I believe HP then eventually bought over 3Com. When I lived in South Africa, I used to use 3Com equipment. It was absolutely fantastic equipment. So when we talk about Ethernet, we talk about something that happens on layer 1. Right in the beginning of this course, I spoke and I told you that in general, when we speak about Ethernet, we always got to talk about something called the OSI model, the OSI model, and that the OSI model is made up of 7 different layers, and it's a conceptual thing. And if you understand that, you understand kind of how networking works. What happens when I press the button, for an email to go out? What actually happens in the background? Well, the best way we describe what happens, or all of what happens, is using the OSI model. So Ethernet kind of works on level 1. That's where you would find layer 1. That's where you would find everything to do with Ethernet. So Ethernet, it's defined by the International Electrical and Electronic Engineers Organization, and they have a particular standard. For Ethernet, they call it 802.3. Wireless, it's 802.11. So there's a whole lot of different standards that are used, but for Ethernet, 802.3, and you can go and look that up on the internet. It uses a common bus where one or many devices can attach to and transmit. So they all talk in Portuguese, right? They can all talk and they can all receive at the same time. It's kind of the de facto standard. You can go almost anywhere, and I've traveled the world. I haven't come across a place that doesn't have Ethernet cabling. It's just so cheap. It's so well understood. It's so easy to install. So Ethernet is really the standard for networking. Here's one of those little complicated things, right? You'll see there in the parentheses it says CSMA-CD. And people say, oh, Ethernet is a CSMA-CD technology. And you go, oh, why did I take this course? really simple. It's not complicated in the least. It stands for Carrier Sense Multiple Access with Collision Detection. Let me break it down for you. The CS, Carrier Sense, it means for an attached device to know when it can transmit. That really means that the devices can sense when it's free to send information, right? Is somebody talking now? Is somebody talk? I'm British. Somebody talk now? No? Now I can talk. Right? Carrier sense. They have this ability. Multiple access, the MA, means many devices can share the same medium. Okay? Many devices can share the same medium. So that's easy. The CD means collision detection. That's all. They can just detect when there's a collision. So I can two people can talk at the same time, and then one steps back and says, "Oh, no, you go first." No, if they're British, no, you go first. No, I insist. Okay, I'll go first. Collision detection. So let me show you here in this particular animation in slide 61. You have a what we call a collision domain, which is a group of computers all sharing the same medium. Remember, we have carrier sense, we have multiple access, multiple devices, carrier sense. You know, they will know when to transmit. So is the network quiet, listening? Yes, it's quiet. Can I cross the road? Yes, I can. So off I go and I cross the road and I send my packet from one side to the other side of the network. Really great. What happens with when I have a collision, right? So I listen, okay, the network is ready, I can send. As I start to send, someone else starts to send as well at exactly the same time. Boom, there's a collision. When there's a collision, it mimics human behavior. They both step back and they have random retry periods. And we're not talking about minutes here, we're talking about milliseconds. So they'll step back and then this one will go off, you know, a millisecond later, that one will go off 2 milliseconds later, and then there's no collision, and then they communicate. So that's kind of where we came from, and but we've made changes, and we've gone further nowadays. Historically, when I started networking, we originally used coax cables, like your cable that you use for your TV antenna or so. Those were coax cables. We've moved way beyond that. The most common standard is the second one, the unshielded twisted pair. That's the stuff when we talk about Ethernet being pervasive all over. That's what we're talking about. And nowadays you have the twin axial for the really, really high speed networks, 40 gigabit per second. So that's the type of stuff that we're using. Ethernet, generally speaking, you have a maximum distance from the device to the switch of 100 meters. And that could be one physical cable that's 100 meters long, or it could be from here to the wall plug, from the wall plug to the wall, to structure to a patch panel, and from there to the switch. 100 meters, that's what you've got. If on some of these, they are less than that. So I'll give you an example. If you look here at this table, Cat5e, that can do between 1 to 5 gigabit per second. It can do 5 gigabit per second at 55 meters and 1 gigabit per second up to 100 meters, right? That's with Cat5e. But look what happens when you go with Cat6 or Cat6a. If you go to Cat6a, you can do 10 gigabit per second up to 100 meters. The cable looks exactly the same on the outside. An Ethernet cable is an Ethernet cable, but on the inside they're shielded. The electric is shielded to prevent interference between one cable and the next. So that then gives us the ability to go these greater speeds. So you get Cat 7, Cat 8. So you see Cat 8 over here is going to operate at 2000 megahertz, but only 30 meters. So we would use these to connect servers together. So servers are all in a particular location, 30 meters. You'll never go more than those 30 meters. So you can do 40 gigabit per second with Cat 8. Other than Ethernet, you also have fiber connections, right? So fiber, gigabit connections, SR and LR are different types, older and the newer types. The great thing about them is that they are immune to electromagnetic interference. So, you know, it doesn't matter if you place them next to power lines. Because it's light, they will not get any interference from anything. So for that reason, they really, really great. So physical connectivity, right? When you connect a wireless network, when somebody says to you, hey, we want to put a wired network in our office, what are the considerations that we need to think about? So, well, we think, well, depending on the size of the network and how many people, we would put at the desktop level gigabit, 1,000 base T is another word for it, gigabit connections. If we have servers and things like that, we might put a 10 gigabit connection to our switches, and then from the switches out onto the internet, if we really need that, we can get a 40 gigabit connection. That would be very expensive, but for an enterprise you could do something like that. So here we go, 1 gigabit for PCs and laptops, 10 for servers, 40. Distance between devices, well, we know that if we're designing a network, we need to think about distances. How big are these distances that we need to cover? So that's important as well. And then money, ching, mullah. We need to think about this. If you got a lot of money, you might want to do fiber. If you don't, definitely Ethernet, and then think about all these other considerations. So when you're thinking about designing a network, these are things that you have to consider, right? When you're thinking about a wireless network, you need to think, where is it going to be used? That's really important. Of course, distance is also important, but what's the design and the purpose? Is it going to be in a stadium where you're going to have, the NFL Super Bowl and 70,000 people sitting in a stadium at the same time watching the same game? Wow, you got to have a serious network. And Extreme, we are so good at that we've actually got the contract to do all the NFL and baseball as well. We do the baseball league as well in the US. We know how to do big venues. So what's the design? What's the purpose? What type of a network is it? Is it a LAN? Is it a WAN? Is it a MAN? A campus LAN? What type of network are we talking about over here that you want to set up? And then device type. So what devices are going to be connecting to your network? Is it machines in a hospital, x-ray machines? Is it fingerprint scanners? So these are all things that we need to think about when we start to think about, Ethernet and cabling, and what is the end use of this? Who's going to use it and how are they going to use it? Those are all things that we need to consider. When you design a network, depending on the size of the network, you can have different access layers, right? When we talk about access layers, is basically at the edge. So the last layer of devices before a consumer touches it or a photocopy machine is plugged into it, right? You can have a situation daisy chain, like you see over here. You can have point to point, so just one talking to one, okay? And then you can have point to multi-point, which is most networks nowadays are designed in that way, point to multi-point. Many devices connecting to one switch. The access layer being the layer that you and I touch, right? So we go to an airport, we sit out, or we go to a coffee shop, we sit down, we open our laptops, we connect to the wireless network. That's happening on the access layer. That wireless device, that's the last device before us. Last device before access layer. But behind that access layer, there's something else. There's another layer. We call that the aggregation layer. So we might use an aggregation layer if, for example, think about a campus network where you have different buildings and you have a data center. So the distance between these is too much. So you go through an aggregation layer and you put in this aggregation layer and feed all the buildings into that particular layer. So here you would expect to find switches with a lot more grunt, a lot more power, with a lot more processing capability, able to handle much bigger loads. And if you need to, and your enterprise is big enough, you might even have a third layer. So you have your access, you have your aggregation layer, and then you have your core. And this is where the really big guys sit that receive all the data from all over the country, from all these branch offices. They all come into a massive big location, and you have the really big expensive toys sitting over there. And that would be what we call the core layer. I'm not going to go into it in much details because we do talk about these concepts as we go along, but it's just to give you an idea that when you start designing networks and you start thinking about computer networks, there's many elements to it. What's the use case? What are the distances? What are the locations? How are these buildings connected? How are these groups? How many people? These are all things that you have to have in your head. And horses for courses, right? It's the right tool for the right job. That's what these things are trying to indicate to you. So we've got to the end of the lesson for today. We've run out of time. I'm going to make a note. I've stopped at slide 75, and when we come back next week, I will give you. We will continue. I'll do a little brief overview of what we've done before, a recap, and then we'll start from this point and we'll go onwards from here. So before you go, I'm going to tell you that I'm going to give you a little bit of homework. It's not a lot. It's not like, oh, pages and pages. It's one slide. It'll come up just now. I'm going to give you one slide. There'll be like 3 or 4 questions on it. That's it. Really simple. Just, when you finish here, go and do it. You'll probably knock it up, within 10 minutes. Really easy. A couple of binary questions and stuff like that. So please do the homework. We will look at the answers in next session next week, and I really look forward to seeing you back here. Invite your friends, tell your friends about this. I hope you've enjoyed it. Go onto social media, tell us how much you liked the course, tell us what you didn't like or what you like. Oh, by the way, I need to tell you, we're going to ask you to do a survey for us to fill in some questions, but I'm actually going to pay you to do that. And you know how? I'm going to give out a Nando's voucher. If you fill out the survey, your name will go into a draw, and we will then pick out from everybody who completed that survey successfully. And please, don't just tick and send it in just so that you can say, I've done that, because rather don't do it. That survey really helps us. It helps us to help you. It helps us to get better. If you tell me, hey, this guy is a terrible teacher, he talks too fast, he talks too loud, he's too intense, then I know next time I've got to tone it down, I've got to change, I've got to talk a little bit slower. It will help you, and it will help other students as well. No, I'm not going to talk in Russian or Spanish. No, don't ask for that. But please do it honestly. It really helps us, and I promise you we will draw, and whoever's name comes out, if you live in a country where they have a Nando's, we will send you a voucher and you can go and have a fantastic meal. So once again, thank you so much for joining. I hope you've really enjoyed it. Like us on Facebook or LinkedIn or any of the social platforms on which we're in. Follow me, follow Extreme. I've loved having you here. I hope you've enjoyed this. I hope you've really learned something. And I really hope you tell people and come back with more friends next week. Remember, this content will be up on the site, and you can go and watch it again. If you want to review something, go and watch it again. Tell your friends, hey, you can go and sign up and you can go and watch the stuff. The course is for free. Give someone an opportunity, give somebody a gift of knowledge, and tell them, hey, come learn. You want to change your career? This is the place. See you next week. Cheers.